they give us a system of nonlinear equation, and we need to describe the type of the x and the y population. So you see that the coefficient here is minus 4x and minus y, so they are both actually declining population. It is naturally declining. There's no term that's x squared, so no terms where x interact with themselves. So naturally declining, and it's exponentially declining. And for this, the coefficient of x, y, so when they interact with each other, for x population, when there is the presence of y, it helps that population, it helps x, it's increase, the rate of change increasing. And for the presence of x, the population y also has a rate of change increasing. So they help each other. So the nature of interaction is cooperation in this case. We first need to find the critical point for this case. Zero, so this gives us x, 2x actually, y minus 2, y, x minus 1. 0 we have the case x equals 0 or y equal to y equal to 0 or x equal to 1. So we have two critical points, so two isolated critical points, 0, 0 and 1, 2. So for the case, let's look at both cases. We need to compute the Jacobian matrix. This is a non-linear system, and it's actually almost linear. Jacobian fx, fy, gx, gy. F is this, y, and g is this. Two y, 4, 2x, y, x minus 1. Let's look at the critical point 0, 0. Jacobian will be minus 4, 0, 1, minus 1. In this case, you see that a lower triangular matrix, minus 4, minus 1, lambda 1 minus 4, or 1, lambda 2 minus 4. We have a sink, nodal sink in this case. So we have two eigenvectors. The first one, lambda 1 equal to minus 1. V1 will be 0, 1. So we multiply 0, 1. We would have 0 minus 1. So it's lambda 1, lambda 2 minus 4, 0, 1, 3. So AB equals 0. A plus 3B, 0. A equal to minus 3B. So minus 3B, B. Eigenvectors minus 3, 1. So V2. It look like this, minus 3 and 1. We can keep us these vectors, and the light look like this. It's a sink, so the other one on 0, on 0 on. It's a sink. v1 lambda 1 minus 1 minus 4, v2 lambda 2 minus 1 minus 4. If it goes to infinity, this one decays, so it's look like this. Close to that is look like this, and far away is spiral to v2. Yeah. So this case is asymptotically stable and in proper nodal sync. Let's do the other one. 1, 2. Have 2 minus 4, 2, 2, 0. Minus 2, 2, 2, 0. Minus 2 minus lambda 2, 2 minus lambda. Determinant lambda square plus 2 lambda minus 4. So we have lambda 1, 2, root 5. So root 5 you have 1 is positive, 1 negative. Saddle point in this case. 0, 0 is a saddle point. Lambda 1. Say AB 0, 0. This one gives us 2A minus B times minus 1 root 5. I choose A to be V1. So it should be 1.24 to 36, and the other one lambda 2 minus 3 to 36. Okay. And the other one, so this is for lambda 1. Lambda 2 minus 1 minus root 5. So about minus 1 minus root 5. 3, 2, 3, 6, 2. 1, 2, 4, 2. So we can grab that. First one is 1.242. Somewhere like here. The other one is minus 3, somewhere like this. And saddle, one negative is the one correspond to V2, lambda 2 here. the other one like this. I think we have enough info to plot all together. 1, 2. This one. Look like this, and the other one is 0, 0. So we all care about close to this. Let's take this circle, join them together. So in this case, let's look at this. We have this line, this separatrix. If the two populations, the initial condition somewhere here, somewhere there, so below this separatrix, they both will eventually die out. But if they start from somewhere there, the initial condition, they have, for example, both of them x has more than 1, y has more than 2, for example, they are here, there, then they will grow unbounded. So if they are in the lower half, if the initial condition is in the lower half, eventually they will both die out. Long term behavior depends on the initial conditions. If the initial condition is on the lower, if x not, y not, so x 0, but the time 0, y at the time 0, below or the separatrix, they will both die out. We have extinction. And if they are above, the initial condition is above the separatrix, then we have unbounded growth. Is above the separatrix, so in this region, both of them will grow unboundedly. Unbounded growth.